our unit on topic 9, which is oxidation and reduction. Okay, so not all reactions involve the transfer of electrons, but when we do have a reaction where electrons are transferred, we can interchange chemical potential energy and electrical energy, which ultimately we call electrochemistry, and there's all sorts of applications of this. Okay, if you are watching this on a device with a battery or that's attached to a power source, I don't know how else you would be watching it, you're using electrochemistry. And so we'll find out about how all that works, or at least start to scratch the surface. Okay, so oxidation and reduction involve a transfer of electrons, and these always occur together. We'll talk about what those are in a minute, but you can't have one without another. And just not every, but a lot of our very important processes are redox reactions. So photosynthesis. Remember, if we don't have photosynthesis, all life ceased to exist on Earth pretty much. Corrosion. Okay, of course, our lives would be a lot easier if things didn't corrode, but that's an electrochemical process or a redox process as well. Okay, so before we can really talk about electrons being transferred, we have to have kind of our accounting method. And so we use oxidation states, and this is our way of figuring out who has what electrons. Now, it's not necessarily what's true in nature, but it works. Okay, so it's kind of a man-made accounting system. So some things to note. If you're going to have a positive oxidation state, you're actually going to write like +2, not just 2, and not 2+, because it's not the actual charge. And this really represents an actual charge, this being the oxidation state. So there are rules for assigning oxidation states. You need to memorize these. Hopefully, as we go through them, you're going to go, oh, okay, well, this is kind of logical. So here are our rules. Number 1, the oxidation state of an atom, an element, an uncombined element, is 0. Okay, so if we have solid sodium, well, it hasn't gained or lost electrons, and so it's at a 0. But even like O2, so molecular oxygen, or O3, ozone, we're still going to say that that's a 0, because if we have 2 oxygen atoms, one of them hasn't gained the electrons from the other, they have equal electronegativities. So there's no net shift of electrons, it's a 0. Okay, but if we have a monatomic ion, the oxidation state is the same as its charge. So Na+, well, its oxidation state is +1. Calcium with a +2 charge is a +2 oxidation state. Okay, in a compound, a neutral compound, all the oxidation numbers are going to add up to 0. And if it's a polyatomic ion, so there's a net charge on it, the sum of those oxidation numbers equals the charge on the ion. Okay, and then there's a few element-specific ones. Fluorine is always -1, okay, in its compounds, not uncombined, but if we have like sodium fluoride, fluorine is going to be a -1. And hydrogen will be a +1 if it's with a non-metal. If it's with a metal, if it's a hydride, like calcium hydride, it'll be a -1. But 99% of what you'll see in this course, hydrogen is a +1. And then oxygen. Oxygen is going to be a -2 in its covalent compounds, except when it's a peroxide, like this is H2O2 hydrogen peroxide, and there it's a -1. Okay, so these rules kind of all stack up on each other. So rule number 1 is where we're going to start in assigning. We'll go like down kind of as a flow chart in terms of assigning these. So let's practice. It says determine the oxidation numbers of nitrogen in the following species. Notice that all of these are, if they're combined, are combined with oxygen or hydrogen. So we're going to use our rules about oxygen and hydrogen to then do some algebra and figure out what the oxidation state is for the nitrogen atom. So in this first one, it's combined N2O4, so oxygen is going to be a -2. And we have 4 -2, so 4 times -2 is -8. All right, and we have 2 nitrogens to go with that. And so our 2 nitrogens combine with -8 to give us a net charge of 0. So 2n minus 8 equals 0. N is going to be +4. All All right, NH3, hydrogen is always a +1. And again, we're going to do kind of some algebra here. So nitrogen plus 3 times 1 is going to equal 0 because there's no charge here. So nitrogen must be a -3. All right, nitric acid. Well, we know that oxygen's a -2 and hydrogen is a +1. So, but all of this is going to equal 0. So 1 plus nitrogen plus 3 times -2 equals 0. And we'd solve for nitrogen. Or we could go, oh, well, that's the nitrate ion. So nitrogen plus 3 times -2 equals -1. Either one of those equations, you'll get +5. Okay. For the record, you're not going to see oxidation states greater than 8. So, you don't even have to take off your shoes to do this sort of algebra. You can do it all just on your fingers or hopefully in your head. Okay, so NO3 negative. Well, here we have oxygen that's a -2 and nitrogen plus our 3 oxygen, so is going to equal -1. So nitrogen plus a -6 equals -1. Nitrogen must be a +5. And lastly, N2, it's uncombined, so it's a 0. Okay. I want you to add this one on to your notes, and I want you to assign these oxidation numbers real quick, and then you can start the video once you've done that. So hopefully you got that oxygen was a -2, but for iron, you might have been stumped and said, well, I'm getting like 8/3. Is that okay? And the answer is yes. Remember, this is not what happens in real life. This is just kind of an accounting system. So how real are oxidation numbers? And is it okay that even if they're not necessarily real, if they're arbitrary or man-made, does it matter since they serve their purpose? Okay, lastly, we've seen Roman numerals in our naming for a long time, and we told you that those Roman numerals on your transition metals represented the charge. Well, that's true, but it's also true that those Roman numerals correspond to the oxidation state. So, and that's actually a slightly more correct version. So FeO, we have iron with a +2 charge, oxygen with a -2. So it's iron 2 oxide. But if we had Fe2O3, it's iron 3 oxide. So this half probably looks fairly familiar, it's straightforward, but let's look over here. In Chem 1, you should have learned MnO4 as the permanganate ion, and a lot of people call it that. However, it's also correct, and what you'll see in IB, to call it the manganate 7 ion. Also, this is potassium dichromate, is what we would have typically called it, but we're going to clarify that it's potassium chromate Vi6 to show you the oxidation number of chromium, because chromium is frequently 6, and by the way, it's frequently 3, and we're going to see those changes later on in this unit. Okay, so there you go, all about oxidation states.